Okay, good afternoon, everybody. I hope everybody's having a wonderful day. So just a quick thing before we get started, just as a reminder, remember your final assignment is due by the end of the 3rd, aka there's that 8:30 rule in effect as well, so you always have until 8:30 in the morning on, I guess it's Saturday. I think it's Saturday is the 4th, until you can submit, just as usual. But anyways, are there any questions or concerns of that kind before we get started? Or give me 2 thumbs up if we're good to go, because I want to kind of pick up to where we were last time. But yeah, if we're fine, don't worry. You can always ask me after or send an email. I'm very happy to answer any questions. So I want to pick up talking a little bit about the relationship Turing machines have with computers. Now, I've talked more broadly about this when I talked about the Church-Turing thesis, right? But I want to mostly focus on the fact that there's a relationship between standard models and computation. I mostly bring this up because probably in the past you've probably studied some algorithms before, but under the purview of something, say, like the random access machine model or RAM model. If not, you may not have known it by that name, but typically most theoreticians like me like using the RAM model very often when analyzing algorithms. But you'll very often run into this in the kind of, like, say if you take a class like CS340 or you're doing analysis of algorithms, usually it's the kind of model you run into where you're counting the instructions and you have a certain set of elementary operations like your arithmetic, assignments, conditions, and so on, and you have certain number of operations are allowed for memory. The underlying model obviously is more like an assembly-like language, but we don't got to worry too much about that. I just mostly want to bridge things that you've seen probably in a previous course before this one. If not, that's okay too. So you may have studied models that are very much like real computers. So for example, a random access machine, or RAM. Not to be confused with RAM memory. I'm not talking about a systems concept. I'm talking about the random access machine model. So this is just, like I said earlier in the course, I said that this is actually, there is an equivalency between Turing machines and the RAM model. So in this sense, you could think of this like a real sequential computer. So in the sense that I'm talking about a computer like this, you can in fact simulate a Turing machine. But there's also a close relationship that they do have as well when it comes to this equivalency from a time complexity standpoint. So a Turing machine can simulate, for example, the RAM, like any given RAM, and do so in time that is polynomial in the number of steps by the computer. So what does that mean? So if the computer performs, say, n steps, you can guarantee that the running time of my simulation via the Turing machine is also going to be polynomial in those number of steps. So this is quite similar to our relationship I established previously involving single-tape Turing machines and multi-tape Turing machines, how you can go from one model to another and you can still maintain some slowdown that might happen when you go between the two models. In this case, it's still polynomial. Just to elaborate on this, if you find yourself curious more about this, the intricacies of this, in the Hopcroft book on chapter 8.6, they describe such a model, and they show that how you can take a basic computer model, and you could simulate it with a multi-tape Turing machine. So I could take a multi-tape Turing machine, I can effectively have a series of tapes, and each one's going to represent an aspect of my operations. There's a lot more details here, and they show you how you can simulate the computer using cubic time. So if there's n moves for the computer, then you could do it with the Turing machine in cubic time. So big O of n cubed time. Now I have a question for you. If I told you that I can do this with a multi-tape Turing machine in n cubed in terms of big O, what can I do with a single tape Turing machine? Can somebody tell me? So if I told you it takes cubic time to do it with the multi-tape Turing machine, how long does it take for if it was a single tape Turing machine? If I were to take what I have here and turn this into a single tape Turing machine? Yes, that's the theorem I'm referring to. So we know, I already said this earlier in the course, that jump is still polynomial, right? So that's the part that I really want you to pay attention to. So if you wanted to do this with a single tape Turing machine, it's actually big O of n to the 6th. Why? Because if I give you a multi-tape Turing machine and it performs, say, m moves, in this case that's n big O of n cubed, then you know it's always going to be that squared. So if it's n cubed all squared is n to the 6th. So these little details are rather helpful for us. So you can see that I can indeed, in polynomial time, still maintain this relationship. So if you know things about algorithms from previous algorithm courses, such as, say, computing a minimum spanning tree or things like that, that notion of polynomial time, it translates to the Turing machine-based way of thinking about it as well, and we still maintain that polynomial slowdown. So just keep that in mind. That's a really important aspect of the connections that you may have seen in a previous algorithms course versus this approach, okay? So you're going to find very much up to this point that I'm going to almost blur the lines between these things. Because if it stays polynomial, if I'm interested in polynomial time algorithms, I could talk about it in the sense that you've seen probably in a previous algorithms class, just writing algorithms like pseudocode, or I could describe it as a Turing machine. You can think of these as different degrees of granularity of how I'm specifying the algorithm to you. Just like if I had a computer system, I could describe it in terms of machine code, the assembly, the programming language, to even more abstract than that. So this is a natural bridge for me to do this. Does everybody see that? So if somebody was talking to you about, oh yeah, I have this algorithm, and they describe it in a language that would be very similar to what a computer would have, like pseudocode, like you've seen probably in analysis of algorithms class, there is no difference when it comes to me saying polynomial time here and polynomial time in, say, when I'm talking about a computer, an algorithm described by something I can use with the RAM model. Okay? So if you're curious about this, a little further beyond this, I think I pointed this out to some parts of the class in the Discord server, that there is a paper that actually does show this relationship. So if you're not satisfied with the description in the Hopcroft book, which I think is pretty accessible, if you find yourself curious about this, there's a paper by Cook and Reckhow from 1973. And it's called time-bounded random access machines. I'll just abbreviate it as RAMs. And they show a connection between a multi-tape Turing machine and the RAM model in this paper. So you pick up the model of computation that makes it easiest to describe your algorithms. So if somebody wants to describe it more in like a programming language-esque way, like with pseudocode, in that sense, you can pick that up. And you still maintain, if you want to talk about polynomial time running times, it doesn't matter. You can talk about it this sense. You can talk about it as a Turing machine. That's one thing I really want you to take from what I'm describing here. Is that clear, everybody? So I've already kind of alluded to this with the Church-Turing thesis, but this is a much more narrow sense. So why? Because I'm going to be interested in describing to you efficient algorithms for solving problems. And usually the delineation between the two is usually by polynomial time versus things that are not that, usually exponential time. So I just want to make sure it's clear. So if we can maintain that a running time stays polynomial, regardless of which of these two main models I'm thinking of, then we're okay. Right? But that delineation is really important sometimes when I describe things in terms of Turing machines. Sometimes I want to describe them on a higher level. And either's okay. That's the big kind of thing I want you to take from this. So the big point I'm getting at is that you're going to find that the line is going to very much blur between these things when I'm going to talk about this. It's a feature. It's not a fault, okay? It's a feature. So that brings me to... Yes? Yes. Yes, yes. So keep in mind it is a generalization. So you can technically have a multi-tape with one tape, and you can have it with 2 tapes and 3 tapes. If you're wondering about this proof, the one that I'm pointing out here, and also in this one, they usually employ about 4 or 5 tapes. Okay. So when it comes to the simulation, though, like I mentioned in a previous lecture, the simulation from a multi-tape to a single tape, it grows quadratically. So the number of moves that happen, it happens quadratically. The proof works essentially like I'm going to simulate the multi-tape Turing machine using multiple tape tracks. And what I do is I just go simply back and forth looking at the tracks in themselves on a given part of the tape. So every time I do, because I can encode each tape cell as essentially an encoding that it's a tuple. But yeah, I talked about this in a previous lecture, but it essentially boils down to that you end up where you have this quadratic blow up. It still stays polynomial in terms of the number of moves. But yeah, if you're curious more about the details for that, I have actually a reference for this one in the notes, if you're curious about that. But yeah, that's an excellent question, by the way. It's something that is relevant to talk about with this kind of stuff. So that brings me to talking about what I'm going to focus on really for the remainder of this course. Is I'm trying to motivate something it's going to talk about this notion of tractability, which is things that we're going to describe as being solvable in polynomial time. Now you may argue, Dan, well, is polynomial really a good representation of efficient? Now, for a tough problem, most certainly it may be. But for very easy problems, maybe not. For example, for certain problems, ones that are really easy to solve, for example, if I gave you an algorithm for trying to find a key in an array, for example, you'd say, okay, an algorithm that runs in linear time, that's quite good. It's just simply scanning over and checking if there's one that exists. For the context of that, linear time is very good. It's a very efficient way of approaching it. However, for something like that kind of problem where I'm searching over just a collection of elements, linear, quadratic, especially in the Turing machine sense, a quadratic might be pretty good. But when we build a much more sophisticated model that can take into account more intricacies, like the RAM model, for example, then you can talk more granular about these things. So, for example, if I wanted to find the key, now if I describe to you a quartic or cubic time algorithm that searches for something in an array, you would say that it's a rather slow algorithm, right? It's not very fast. However, we're going to mostly use this definition to talk more about broader classes of problems, usually ones that are actually, for our best knowledge, have running times that are exponential. So it's often a nice classification for talking about our easier problems to solve versus these tougher problems to solve, as we're going to see. So I want to talk a little bit about the former. So many decision problems. So whenever I refer to a problem, by the way, at this stage, presume I'm talking about a decision problem, okay? So when I say problem, just think decision problem. Means it has yes, no answers, okay? So it's either in the language or it's not in the language. Or it may be complete garbage and it's not in the language. So at least in our framework here, okay? So many decision problems belong to time. Remember, I defined this last day. Time n to the k for some k greater or equal to 0. Right? Last day I showed you a Turing machine that can decide the language where I had an equal numbers of zeros and ones where all the zeros preceded all the ones. So I showed you how you could do that in quadratic time with respect to a Turing machine description, right? So I must stress that when you go from different models, for example, the RAM model, the operations can go much quicker, right? That's why the difference between these two. So a Turing machine, just to be very clear, if you think about what I just described here, a Turing machine trying to simulate a computer is very slow, okay? It's not practical. So that's why we usually use things like the RAM model, because they tend to describe what a computer does much more accurately, at least our real computers in quotation marks. So that's why usually you don't see the Turing machines unless you take things from a more theoretic level at the bottom, depending on what kind of program you come out of. So I want to talk about some examples. So earlier on in the course, I told you, for example, so given a context-free language L is input string W in the language. So I told you that there is actually a way to determine this, right? And I could do this in polynomial time. So any language or problem, however you would like to talk about it, that has a polynomial time algorithm or a Turing machine whose time complexity with respect to the input length is a polynomial or is bounded by a polynomial. Well, it most certainly sits in here. So this is one that we most certainly talked about, but I didn't describe the algorithm to you. I told you it uses dynamic programming. So it's, for example, the CYK algorithm can be used to decide this decision problem. So notice that I framed it in terms of a question. This is a nice, easy way to see yes, it does, or no, it does not. So how about another one? Let's talk about something that you may have seen in a previous computer science class. Given a directed graph, G, and vertices S and T in the graph, is there a directed path? Is there a directed path from S to T? So could somebody describe to me an algorithm that could decide if there is a directed path from S to T in a graph? Like, you could even give me just the overview or high-level way of describing this. So what kind of approach would you take? Just think, you don't have to describe to me a Turing machine to do this. Just describe to me in a very high-level way. You don't have to, it doesn't have to be the exact specification. Just somebody, I'm certain somebody that's been through 340, if anybody's here that's been through 340, will know how to do this. Yeah, you traverse the graph. Can somebody tell me a way I could traverse the graph? I'll give you a hint. It starts with a D. Starts with a D. Yeah, I could do depth first search, for example, here. So I can use depth first search to help me do this. So I could say use a variant of depth first search. And if you use a variant of depth first search, if you encounter this path from S to T, then you would answer yes, right? However, depth first search will explore the entire graph, and if it does not compute a path from S to T, either it doesn't run, so you'd start this at S and you'd work your way to T. If you don't find T, then you answer no, right? So this is another one that would sit inside of here. Because if you're wondering, depth first search, if you think about it from more of the RAM-based model analysis, it actually runs in time linear in the number of vertices and number of edges, big O of n plus m. So if you're curious about that, it's not going to be too important for us. I'm just giving some examples here. So here's another one. This is one you may have seen. It's okay if you haven't. Yes? Yes, so I must stress one other detail that you'll notice that I didn't put here explicitly, right? Here, notice that the n here, there is no n specifically named here. However, the way you would encode this, if you're thinking about it from a Turing machine standpoint, is the encoding would be, in fact, the encoding of all the vertices. Each has a label. And then you have to list all the edges. So now you can always pick up an encoding scheme and say, okay, I'm always going to number the vertices from like 1 up to n. And I can have it so I can code each of the edges using separators, kind of like our Turing machine-based approach. Remember where I encoded the Turing machine? You can do the exact same thing with a graph, believe it or not. And in fact, if you're thinking about it from a much deeper level, you can always encode the binary representation of the graph in this way as well. But yeah, so if you're wondering what n is there in terms of this, this would be the input's length. So here it would end up being something where n is going to be something that's big O of the encoding of the numbers that are going to represent the labels, plus the encoding of the edges. Now, there's some technical details actually, and I like that you brought this up because it is actually a very important technical detail. So if you're curious more about this, the Sipser book actually goes into more detail about an example like this one, but I'll point you to the Hopcroft book because they really, they drill down this hardcore. I'll mention it when I give you this third example here, okay? So if you find yourself really just curious about how exactly you do this, if you think about it from a Turing machine standpoint, I'm not going to focus so much on that here, but the point is that this is the input length. Notice that in this problem, it's very clear what it is. Okay, there's some input string, and I need to determine if it's in this language or not, right? We've done things like that before. Here, you would have to encode the graph, so you would have what would tantamount to the encoding of the graph, encoding of a vertex, and another vertex being encoded. So you'd have a triple at least. But yeah, so hopefully that clarifies things a little further. So when I use n here, this n is not the same as the number of vertices when I described it here. N would be the number of vertices in the context of a graph, but you would have to give it a different name. Some people, for example, will, instead of using x here, they'll say, okay, if the input is x, they'll put bars around it to refer to it as the input size. So some people would refer to the input length as something called input size. And this would be the input. So for example, this would be your graph, this would be your vertex and another vertex, and this would be the length of its encoding. So this is just to not create confusion when you talk about another n or something like that. Does that clarify things a little further? No, wonderful question, by the way. That's a very nice technical kind of question that I appreciate a lot. It helps actually, these are the kinds of questions that really benefit the class because they're very specific and they actually do address things we're exactly talking about. So I'm very thankful for those kind of questions. So, yeah, Dijkstra's algorithm. Yeah, you could use Dijkstra's algorithm to do this. I would not recommend it. I would recommend using a graph traversal approach instead because notice this graph isn't weighted at all. So it's just simply it's just a directed graph. We don't care about if there's any costs or weights on them. Dijkstra would be what you would use if you had weights on the edges. But you can use Dijkstra. It's just a little slower. But you can. I believe you can for this one here. But let me give you another example. And I want to do this one deliberately in this way. Actually, let me write it over there. Let me just write this over on that board because I'm running out of space here. And I want to give you some mercy when it comes to that. So here's a third example. So given a weighted connected graph. You can give it a name if you feel like it. And an integer k, is there a minimum spanning tree? You may have heard of what a minimum spanning tree is. Not that's okay. A minimum spanning tree whose total cost is at most k. Now, you may have seen a problem like this possibly in previous studies. It's okay if you haven't seen this before. I'm not going to worry too much about the definitions here. I just want to make sure you see the idea here is that I'm talking about decision problems. So if I give you a connected graph, a weighted connected graph, so remember, this is the case where you actually have numbers on the edges. And we're assuming that there exists a path from every two vertices in this graph. And we have an integer k. I want to ask, is there a minimum spanning tree whose total cost is at most k? So if I think about it like this, now you may have seen this problem written in a different way. What have you typically seen this problem written as? Think about the kind of problem you may have seen it like. Is it a decision problem the way you normally see it, or do you see it as something else? The problem formulation matters. Yeah, you see it as an optimization problem. Usually you're told, hey, given this graph, compute for me a minimum spanning tree, right? They want you to get the actual tree or even its value. But this right here is actually just the decision version of this problem. So I ask, given a weighted connected graph in integer k, and I'm asking, because this is a minimization problem, I want to know if there's in fact, I don't even need the minimum part here. Let's get rid of the minimum part. We don't need that. Is there a spanning tree whose total cost is at most k? So now you can either ask, yes, there is a spanning tree. If I add up the weights on the edges in this tree, it's at most k. If that is indeed the case, you can say yes, if it's at most k. Otherwise, the answer is no, right? So I have a question for you. Can somebody answer this for me? How can I use this to help me solve the optimization problem? So it was alluded that usually this is described as an optimization problem, but does anybody have any good guesses on how I could do that? Yes. Yeah, no, very good, very good. So notice that this k actually plays a very close relationship with computing the optimal answer, because if I can find the smallest possible k that I can use, such that it gives me a yes answer, then most certainly that has to be the case that it is, in fact, the smallest total cost possible, which by definition is a minimum spanning tree. Does everybody see that? So one way you can go about this is the way I wouldn't recommend doing it, is you can always start off by saying, okay, let's start off with, assuming the weights were all positive, you can start with k, then 2, sorry, k is 1, then 2, then 3, then 4, all the way up to some maximum number, say in our case, whatever the max weight is, times the number of vertices or something, or let's go number of edges. So you can do something like this, and repeatedly ask this question over and over again. And you just keep it for the first time you encounter the smallest k. So you just keep the smallest k, right? So that's one way you could do this. Does anybody see any smarter way of doing this? So based on what you'd said earlier, I think there's a very nice idea I could do. Yes, so I will tell you up front that if you think about this k, so I can answer, so when I did this over here, so for example, if I told you that, oh yeah, the minimum, like the spanning tree's total cost, if I find out that there's one with 3, then it must be that the one for 2 most certainly did not have a spanning tree. So in these cases, the answer would be no. Then everything after this would be yes. So every single time I give you a k, it it would answer yes for all the other ones. So does this look like something that's ordered? Like a fancy way of describing this would be that I would tell you that the answer is monotonic. So the other way you could describe it is that the objective, so my cost here actually grows, it goes like this. There's a very special thing you can do with algorithms that essentially, that if you cast them like this, that you can use an algorithm that maybe one of the first set of algorithms you may have learned in your studies. That searches, that you can use to search an array that's sorted. Does anybody see how I could adapt something like that here? Does anyone have any ideas of which algorithm I'm talking about? This is more of an aside, by the way. I'm just trying to show you a connection between optimization problems and decision problems. So you think about that as linear search, where I'm incrementally changing k, going up by 1. So suppose now I wanted to get it faster. I want to do this faster. Does anybody have any ideas? What's another algorithm you know for searching an array? But in this case, it's sorted. Binary search, yeah. So for example here, you could just do binary search, and you could play this guessing game. So you would just say, for example, you'd start somewhere in the middle here, and then you just simply say, okay, did I get a yes answer? If I get a yes answer, then most certainly I could try guessing on the smaller half. And then I could ask yes or no. If I get a no, then most certainly the guess means that I need to guess higher, right? So I'm just going to say binary search, play a guessing game. And this is often a very handy strategy, by the way. Just as more of an aside, to find smallest k. So if you do use this process, you can do this with many, many optimization problems. So if you ever find yourself looking at an optimization problem, what you can normally do is you can cast it like this, and then you can use a binary search process like that. If you look at the time complexity, the growth of the running time will actually be based on how many times you run the iterations of this guessing game, which is going to be logarithmic in the number of possible guesses you can make. So if I told you it's the maximum number of the max weight times the number of edges, now it's going to be logarithmic in the max weight plus the logarithm of the number of edges, which that's pretty good, right? But that's more of an aside. So this is an aside. I will not ask you about this, but I just want you to be I want to be very clear that there is a connection between optimization problems and decision problems. So do not get misled by me saying, oh, all I'm asking are yes or no answers. There's very natural ways of talking about them as decision problems, then recasting those optimization problems like this. There's in fact a whole area of discussing about optimization problems in relation to decision problems. If I, for example, show you that there is an algorithm that runs in polynomial time for an optimization problem, if I can cast it like this, and I could show you that it sits in that class that I have over there, the time n to the k, then I could tell you that yes, it sits in that class as a decision problem. We call it this decision variant. But end of side discussion. So do you have a general gist of some problems that we can efficiently solve? Has everybody got a good kind of feel on that? You've studied many problems that can be cast as decision problems that actually have very efficient algorithms. In fact, we're just going to be relaxing that up to the point of a polynomial. Okay, so if we're okay with that, the point is that you've studied many of these kind of problems. So what will be of interest to us are all decision problems, or if you want to think about them as languages, that's another way you can go about this. Languages. You're going to find these very much blur. Like I said, there's a natural correspondence between the two. Are all of these that are solvable, and when I say solvable, I'm meaning decidable. in deterministic polynomial time. And this is, we're going to define one very important class for us. It's going to be called P. It's just called P. It stands for polynomial. So here's the formal definition of P. P is the union over all integer k. So for each integer k, or I consider, so for, that's what I wrote earlier, right? For some k, so I go over all the k's, and for each one of them, I give you this. So I'm saying that I'm going to lump all these together in one big bucket, and I'm going to call it P. So if your language sits in here, then we say it belongs to P. So this is the class of deterministic polynomial time solvable problems. So just to be clear what I mean, so that is, P is the class of languages, problems. And remember, I must stress that this is defined with respect to decision problems. So when we talk about this, we're talking about decision problems or languages. It's a common mistake to presume otherwise. But there's a lot of superficialities that you can get around it. I just must stress that. Problems that are decidable in polynomial time on a single tape deterministic Turing machine M. And like I said, there's a lot of connections that get you from a single tape Turing machine up to a computer. So, if you're thinking about this, here's more the higher way of me describing this. In other words, given a decision problem, pi is in P if there exists a, just going to write it up here. There exists a polynomial P. This is a lowercase p, just to be clear. So that on input W, of length n, there is an algorithm. So remember, when I say that, I'm usually referring to a decider that gives, I'm running out of space. This gives a yes answer to W in time at most P of n, without big O there. So let me reiterate that because I'm sort of running out of space over here. In other words, given a decision problem pi is in P if there exists a polynomial P, lowercase p, so that on input W of length n, there is an algorithm that gives a yes answer to W in time at most P of n. Or this is lowercase p again. So this is just another way of reiterating what I wrote here and what I said previously. So we'll usually think about this when we talk about decision problems as yes instances and no instances, and checking yes instances or saying that no, that's a bunch of bull. So are there any questions about P? So if you're ever not sure about this, just appeal to this definition. It's nice and simple. But we have an exact way of describing all of those decision problems with polynomial time algorithms with respect to their input size or input length. Okay, so if we're okay with this, let's proceed. So I'm going to kind of touch on a couple of quick things, just because I want to deviate us towards another class that will be of interest for us. We may or may not have examples to really kind of walk us through it. If not, we'll do those next day. So I've described this class called P. Now, I would like to have some way of talking about those non-deterministic Turing machines. I'm going to refer back to something I said earlier in the course where I said I was going to plant a seed for you. And I showed you that there's a computational equivalency between non-deterministic Turing machines and the Turing machines. Does everybody remember that? That there is this equivalency that exists between the non-deterministic Turing machine and the Turing machines when we have them being purely deterministic, right? But we had this thing that happened in the proof. Does anybody remember what happened? Remember I had that whole that approach where I had a queue and I was going through in a breadth-wise manner through the computational tree when I was simulating it? There was some issue that came up there. Does anybody remember what that was? Do we have the polynomial slowdown there? The answer is, unfortunately, we do not have the polynomial slowdown. We have an exponential blow-up. So here's a theorem. I'm going to give you just the theorem. I have a sketch in the notes, but I refer you to specific theorems if you're curious about the full proofs. So here's a theorem. Suppose complexity function t of n, or t, is greater or equal to n for all n greater or equal to 1. Every t time, not to be confused with t time, it's our complexity function. So if I gave you a non-deterministic Turing machine that runs in big O of t, it has an equivalent, 2 to the power of big O of t time single tape deterministic Turing machine. And we talked actually about this proof. So I gave you a sketch of this actually in a previous lecture. And I talked about how they had this exponential blow-up. This is the exponential blow-up, okay? So when I want to talk about deterministic Turing machine versus non-deterministic Turing machine, we know that there's an equivalent non-deterministic Turing machine, but if I want to get that in a deterministic way, remember that non-deterministic Turing machine is a bunch of magic, man. It's able to have this ability to make perfect guesses, right? That we end up having this blow up in terms of how long it takes if I think about it as a deterministic Turing machine. However, it seems very interesting in its own right that can we do any better than this for this proof? And nobody knows how to do that. Maybe incrementally, but it's still exponential. But we don't know how to do that. So we might want to ask questions about this, because there's two interesting facts about this that I want to kind of allude to. There is a wide chasm. Just think of it as just a rift, a wide chasm between problems or languages decidable in polynomial time. Like, there just seems to be this case. For example, we're going to see a couple of problems depending on how much time we have. We probably won't, but if not, we'll see it next time. We're going to see some problems that do, in fact, their best known algorithms all take exponential time. But for a non-deterministic Turing machine, if you think about this construction here, if I do, say, do t of n time for the non-deterministic Turing machine, notice that there's an equivalency between this. So if I told you that I had an exponential running time for one of my algorithms, here's the way you could think about this. Think about this the other direction. So if I give you some algorithm that runs in a time exponential in the length, then there's going to be one that's not going to be exponential, right? So I want you to think about that. That's kind of strange, right? So there's a wide chasm between these two in decidable in polynomial time and exponential time. This is actually why you'll find very often people will tell you efficient means polynomial. That's usually what they're trying to tell you, is that there's a chasm between them. When you study many problems, you find out that there seems to be this separation that happens. It's not, in a lot of problems it is not like that, but many classic problems have this phenomenon. And we don't have really the best of answers for this. There's a lot of theoreticians that do think about these kind of things. But this is also something that you see in the construction. So seen in this theorem. We see that in this theorem. So what I'm going to do is I'm going to define another class, and this one we'll focus more on next time. We're going to define another class of problems solvable or decidable in non-deterministic polynomial time. And here's the definition of what I'm going to refer to as NP. So here's the definition. Just like with P, I'm going to have a union for each one of my integers k. I'm going to encapsulate all the languages or decision problems, however you'd like to look at this, that could be solved or decided by a non-deterministic Turing machine in n to the k time in terms of big O. So this is a formal definition for NP. So just plain language explanation. That is, NP is the class of languages, problems that are decidable in polynomial time. And usually when I say polynomial time, I'm suppressing the with respect to the input length when I say these things. Decidable in polynomial time on a non-deterministic Turing machine. So that's what NP is. Now, next time I'm going to show you actually an equivalent way of defining NP. It's going to be based on something called a verifier. And I find very often with students, they usually the verifying or verifier approach to defining what you can call and prove a problem in NP is a little easier to imagine. as more of a game that you play where somebody presents you a possible answer and your job is to check it. It has a natural correspondence with the non-deterministic Turing machines. So when we come back, we'll talk more about NP, and we'll be building ourselves up to something a little bit more interesting about NP in itself, okay? So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.